Finally, we are ready to talk about vector spaces. So what are vector spaces? In our study of vectors in Rn, we could add them or multiply by scalars. So, and when we manipulated those expressions, we make sort of perhaps subconsciously the use of the fact that addition and multiplication behave as they do for usual numbers. So the notion of vector space axiomatizes the validity of these properties. To put differently, a vector space is something whose elements can be algebraically manipulated like vectors in Rn. Let's define them. So the data of an R vector space is a set V equipped with a distinguished element 0 and two maps, addition and multiplication. This data determines the vector space if it obeys the following rules. So multiplication by the scalar. So the addition is associative, commutative, and V plus 0 is equal to V. And multiplication by scalar is associative. 1 multiplied by any vector is this vector itself, and 0 multiplied by vectors is equal to 0 vector. And also distribution with multiplication by scalar and multiplication by the vector. So is Rn a vector space? Well, that depends on what you mean by Rn. If we just mean the set, then we haven't defined the vector space yet. We haven't given the required data of a 0 vector or the addition law or the scalar multiplication law. To meet the criteria of this definition, we need to define a 0 vector, which is just a vector whose all components are 0. There are n of them. Addition, so we add vectors component-wise, like this. Multiplication, so multiplying the vector with components v1 through vn by scalar c is just multiplying by the scalar every component of the vector. And then we need to check the 7 axioms from the previous slide. So a 0 vector is this, is the vector with n zeros. Addition works like this, multiplication works like that. Is this a vector space? Of course, yeah, that follows from the definition. That's what we just did. As in this case, everyone understands what the vector, 0 vector addition and multiplication are meant to be. They may not be mentioned explicitly, and then the structure of the vector space is naturally ascribed to the set. So Rn is a vector space, unless specified otherwise. So in ancient Greece, they didn't really think about coordinates as we know them now. Rn would not have been a natural notion. And instead they have geometry. They talked about space, planes, lines, points, circles, etc. So this is believed to be Euclid himself. And then they drew pictures like this, something that you probably did in high school geometry class. So could you get Euclid to think of a plane as a vector space? Well, first we need to choose a point to call a 0. And that's no problem because you can just pick any one and declare it to be 0. And then you need to say how to add points. And we do this by the parallelogram rule, which is, of course, the coordinate-free geometric notion. So we could construct a parallelogram with a compass and straight edge, like this. Now we need to say how to scale vectors, how to multiply them by scalar. Now, there's this trick over here again, coming from high school geometry, which of course was developed in ancient Greece. So look at the picture on the left, and then you can prove that the length of segments AP times PD is equal to CP times PB, right? So say P is the 0 vector. So like you would put your origin of coordinates here. And then to rescale vector C by factor lambda, by scalar lambda, we construct the segment PA of length 1, right? So we need this to be equal to 1, and PD of length lambda, right? So then we would draw the circle like this. And then find what the circle through ACD meets the line PC. And the point B will be the rescaling. So it's actually pretty good. So ancient Greeks already pretty advanced about this point. However, there's a little subtlety here. So it's true that with this simple tools, you can construct a rescale by any given length, but so how the length's given to you in the first place? Like, how do you know by which lambda you want to rescale the vector? And it turns out that not all real numbers can be constructed with a compass and a straight edge. So if you like, you can take this class 113, where we talk a bit about abstract algebra and then which numbers you can, which numbers you cannot construct this way. Okay, now, so having said how to define addition and scalar multiplication, we still have to check that they satisfy the axioms. So, and we can do it geometrically, right? So an appropriate choice of coordinates on the plane gives an identification with R2, but note that this can be done in many different ways. Okay, so now let's talk about functions. We have a set of functions f from R to R. So there's a 0 function 0 defined by, it sends every point to 0. Then we can add functions like this. So f plus g of x is equal to f of x plus g of x. So the left-hand side, so you think of functions as points in the vector space. So it's a new notion here. So we can scale a function. We define CF as, so when we evaluate this function, when we calculate its value at point x, it's defined like this. Is this a vector space? Well, we can check the axioms, right? So look, here are the 7 axioms where you can account from the definition of the vector space. Well, and then take 3 functions. So clearly the associativity property works. So you can just evaluate them like this, right? So it's f plus gh of x is equal to f of x plus this, and then of course it's the same if we do it the other way around. And similarly, yeah, so this also works. So these are all equal to the same thing. So yeah, associativity works. Now check that f plus 0 is equal to f, right? So that follows directly from the definition of a 0 function. So it just sends everything to 0. So those should be equal to, yeah, so f plus 0 of x is equal to f of x plus 0 of x. And then from the definition of the 0 function, you just add 0, which means that you add, it's equal to f of x. Finally, we need to check this property. So again, we evaluate those functions. They have to equal when evaluated at any point x in R. And that's clearly the case, right? So C plus D f everything of x, right, is equal to C plus D f of x and so on. So you can see that those properties that are clearly satisfied. And then similarly, you can check the remaining axioms. So by expanding out the definitions and then appealing to the corresponding fact about ordinary numbers. So yeah, it's a good exercise to try this at home, in addition to the homework. Given any set S and any vector space V, we could have said that the same words for any set of functions from S to V, not necessarily functions from R to R. So we just say that we would apply a vector space axioms to V. Example, so take S to be the set of n numbers, n integers from 1 to n, and then define functions from S to R, which is sort of more or less the same as the n tuplets of real numbers, right? So functions from the set into R, which is so set of functions, right? From those to R, we can identify with Rn. So this it will be the vector space which will show functions from S into R. So we need to specify, we need to sort of make it more precise soon, but you can see how, maybe you can try to guess how this isomorphism works out. Let's talk about subspaces. If V is a vector space, we say a subset W of V is a subspace if zero vector is inside W. The sum of any two elements in W is in W, so it's closed under the addition, and scalar multiplication. So any scalar multiple of an element in W is in W. Yeah, so we've seen this, how this works for Rn, but now we can sort of generalize it to an abstract vector space. So a fact about subspaces is that if V is a subspace of W is a subspace of V, then W is itself a vector space using the operations inherited from V. Why? Well, first, the definition ensures that addition and scalar multiplication make sense when restricted to W. And the axioms hold for elements of W because they held for any elements of V, and W is a subset of V. So let's look at some examples here. Is this a subspace of R3? Just zero vector? Yes, right, because it obviously satisfies all the axioms. A single point other than zero? Well, that's a negative, right? Because, for example, zero vector does not belong to this set. A line through the origin? Yes, it does. We check that. A line not through the origin? No, because it, for example, does not contain zero. A union of lines through the origin? Also no, because it's not closed under the addition of vectors, right? So it's closed under the scaling, but it's not closed under the addition of vectors. A circle through the origin? Also no, due to many reasons. Plane through origin, it's true. And intersections of planes through the origin. Yeah, so you can also check that this is also true, right? Because whenever you have two vectors inside each plane, there are some stays, the linear combination stays in that plane. So kind of, therefore, yeah, so this will be this will be the case here. Let's talk about subspaces of function space. So some subspaces of vector space of all functions from R to R. Continuous functions, right? So if you have two functions, two continuous functions, you can add them, you can multiply them by the number, they remain continuous. Zero is a continuous function, and so on. Differentiable functions, same true here. So if you remember all the theorems of calculus, if you know functions f and g are differentiable, that so is their linear combination. And then continuously differentiable functions, and so on. So the various classes of functions, right? So Cn, right? So where C stands for the continuity of the nth derivative. And yeah, all the way to C infinity. Polynomial functions, right? So when you add polynomials, you get a polynomial. Zero is a polynomial, and so on. Polynomial functions of degree at most n, right? So when you add polynomials, the degree cannot increase, or when you multiply it by a scalar. Okay, so which of those subspaces of the vector space which of these are subspaces of the space of functions from R to R? Zero itself? Yes, again, so it satisfies all the axioms. Single function other than zero? No, because it does not contain the zero function. Functions which are zero at all integers? Yep, you can check that. It's an interest. So it's the function which is defined on sort of. So this property is inherited by the addition. Function satisfying f of x is equal to f of x plus 1. Yes, these are periodic functions, right? Function satisfying this differential equation, second derivative of f of x is equal to x times f of x. Yeah, that is also true. It's just a subset of functions which satisfy this equation. Functions satisfying this one, no, right? Because it does not. This set does not contain the origin. Does not contain 0, 0. Functions equal to their own square also no, right? It's easy to check that the linearity properties does not hold. Functions, you know how to write down. Yeah, pretty much, yes. So whichever function has an explicit presentation, you should be able to form a vector space out of them. Okay, so given a vector space V and vectors V1 through Vn and constants C1 through Cn in R, we can name this element the linear combination of the vectors with coefficients in V like this. And the set of all linear combinations is the linear span of those vectors. So we talked about this already in the case of Rn, and as you can see, the definition for an abstract vector space is literally the same. Linear transformations. So if V and W are vector spaces, a function t from V to W is said to be a linear transformation if it satisfies this property. So it's linear like this. So t of Cv plus C prime V prime is equal to C t of V plus C prime t of V prime for all C and C prime in R and all V and V prime in V. So we already met this in Rn. Subspaces from linear transformations. So the range or the image of a subspace. So take a linear transformation T from V to W. Now, if the type of W and W prime are in the range, it means that there must be V and V prime, which are pre-images of those vectors. And for any constants C and D, we have this property over here. So this is also in the range. So we've seen this argument before for Rn, and here it works the same way here. So range is a vector subspace. It's a subspace. Null space or kernel. So take a set of all vectors V such that T of V is equal to 0 is equal to T of V prime. Then for any two constants, this linear combination and its T of this linear combination is equal to 0. So therefore, it also belongs to the kernel, and it forms. Therefore, the null space or the kernel is a subspace. Okay, another example: the derivative. So think of differentiable functions, real value differentiable functions, and this linear transformation that takes a function to its derivative. Well, as you know from calculus, we can just have this property, right? So the derivative of AF plus BG is equal to AF prime plus BG prime. Now, the kernel of this linear transformations, if these linear transformations is the constant functions, right? All constant functions because they're sent to 0 by the derivative. And so, yeah. Now, the image is not really easy to describe in these terms. Okay, now the definite integral. So say we have an integral from R to S, which sets continuous functions, those which you can integrate from R to R into R, right? So to the value of this integral. So we define this operation. Well, it's a linear transformation, right? So take two functions, two constants, And then, well, again, from another theorem of calculus, this formula holds, right? So the integral is a linear transformation. The kernel are the functions whose average value over this interval. So there's a type of R to S is equal to 0. And the image is the whole R. Another example, the evaluation at 0. So take all the functions and then assign them, map them to R, which assigns a function its value at x equals 0. Let's check linearity, take two functions, take two constants. And then, well, so clearly this is true. So AF plus BG of 0 is equal to A of 0 plus BG of 0. And the kernel of this transformation are the functions that vanish at x equal to 0. Again, the image is R. So this is what in physics called the delta function, right? So it's a linear functional that's defined like this, which is you can formally write like integral f of x delta of x dx, and delta of x is so-called Dirac delta function, which is mathematically is defined like this, right? It's the it's a linear transformation that evaluates functions at x equals to 0.